Hello and welcome to another presentation, this time on differentiation. We're going to be looking at chain rule, product rule and quotient rule, and we'll probably get a chance to look at a exam question at the end as well, so we can see it in action. Now this will probably be just jogging your memory, and I'm sure these examples won't tax you too much, but let's have a quick look at the chain rule. Now what is the chain rule used for? Well, it's for when we have a function of a function. Now what does that mean? Well, when you see the chain rule written down, it's not really very instructive for what situation it's used in. So I'm going to actually write out the situation it's used for. It's used for this kind of situation. If you've got y equals f of, open a square bracket, g of x. That's a situation where we might use the chain rule, where we have a function of another function. And I can actually write the chain rule down in an alternative way. I could write it down like this. Then dy by dx would equal, differentiate within the function, differentiate g in other words, giving us g dash of x, and then multiply that by f of bracket, f dash, sorry, we're going to differentiate the function, leaving the other function alone. So in some ways, and sorry, my dashes should both be going in the same direction there. Those dashes are denoting that we've been differentiating. Yeah, in some ways this looks a bit more confusing, and that's why you normally see it written down as we've written it on the left hand side there, just here. You normally see it written down like that in the formula book. And that's the way Leibniz first expressed it. The reason why it works as well, and it looks real obvious here, is because for any kind of differentiation, when you've got d something by d something else, any kind of differentiate one variable with respect to another, you can treat them like fractions, and the chain rule is a perfect example of that. But perhaps the way I've written it down on the right might make things a little bit easier when I talk about what I call quick chain rule. Okay, with each one of these few questions, I'm going to show you the slow way of doing it and the quick way of doing it. Slow chain rule, and this is just really me who uses this way of expressing it, I guess. I call slow chain rule the way where you express everything very slowly and very carefully. We might call this y equals u cubed, where u equals 3x squared plus 5x. And then you find dy by du, and dy by du is going to be 3u squared naturally, and then we find du by dx, and that's going to equal 6x plus 5. And then at the end, well, the rule on the left hand side is clearly explaining that we need to multiply these results, so we get dy by dx equals 3u squared multiplied by 6x plus 5, which must go in brackets. And therefore that is the same when you get rid of the u's, because we're just introduced to help us solve this problem. We're going to get 3 times by 3x squared plus 5x all squared multiplied by 6x plus 5. Now, like I say, I describe that as slow chain rule, doing it nice and carefully and setting it out by, you know, essentially renaming part of the function within the function as u, and then writing y equals, you know, the function of u, and then u equals the function of x. But really I hope you can see, well, you might see in the next part, why it might be more useful and more helpful to look at the right hand side way of understanding it. Now this is where I come to quick chain rule. I'm going to do exactly the same problem, but this time I'm going to try and do it quickly. Now my other alternative way of thinking about it is like this. I just differentiate within the function first. That gives me, now I ignore the cubed in other words, and I differentiate 3x squared plus 5x. That differentiates to 6x plus 5. And then I'm going to be multiplying that by whatever stuff, and I call this this bit here, I refer to it as stuff in my lessons. I now differentiate stuff cubed. Now stuff cubed would differentiate to 3 times the stuff, and the stuff stays the same, I don't change that, squared. and I get exactly the same answer. It just perhaps looks a little bit different. You might wish to put the 3 in the 6x plus 5, giving 18x plus 15 times by 3x squared plus 5 squared. You might prefer, it's really up to you. I suppose it's a bit nicer really having the 3 factorised out and sitting at the start. But there we go, exactly the same answer. Let's do the same thing for question 2. Now it might not be obvious initially why question 2 is a chain rule problem. You might immediately think this is quotient rule. Well, it can certainly be done with quotient rule. We have a quotient there, and something else you might be thinking is that this is indeed cosec kx, and you'd be right to think that it is cosec kx. So we're going to find out what cosec kx differentiates to, which is actually in the formula book. Okay, let's do it slowly. Let's firstly do it by renaming this function sine kx, but to the -1. And then it will become obvious why this is appropriate for chain rule, because it's a function of a function. Let's go straight into the quick chain rule way of doing it. What we're going to do is we're going to, well, maybe it might be easy. Well, no, I'll do it quick way. Sorry, I am so indecisive. Okay, I'm looking for dy by dx here. Let's differentiate within the function first. Sine kx differentiates to k cos kx. Let's put that in brackets. And then we're going to be multiplying that by what stuff to the -1 differentiates to. And that would differentiate to a minus the stuff to the -2. And so we're going to end up with here, I'll try and write it down a bit neater now, k cos kx over sine kx all squared, and we need a minus in there, which I'll put at the start. By the way, just to show you, you get the same answer as the one in the formula book. That will give you minus k times by cos kx over sine kx times by 1 over sine kx. I always like to show students that you do get the same answer as the one in the formula book, or they start, you know, getting worried. Bless them. And it's a good idea to remind them anyway about reciprocal trig functions. And that's going to give me minus k cot kx cosec kx, which is as it appears, I believe, in the formula book. So there we go, we found a derivative of cosec kx, and you can use that to find all the reciprocal trig functions in the same approach, although you might prefer to use quotient rule for some of them, and that's fine. Okay, let's have a look at the last one. We're going to be looking at ln tan x. This one's actually quite easy, provided you already know what tan x differentiates to. And tan x does in fact differentiate to sec squared x. So, knowing that, let's try and use quick chain rule. Because I've got to be honest, slow chain rule, I do use it sometimes if the function's really complicated, but if the function is relatively straightforward, they need to get really good at being happy and comfortable with employing chain rule in their head, as it were. So once again, we're going to differentiate within the function. So I'm going to differentiate tan x first, and that differentiates to, as I say, sec squared x. They do get told that in the formula book as well, but they can be asked to prove it as well, and it's not too difficult to prove it. In fact, we're going to prove it in a few moments in quotient rule. Okay, right, so now let's differentiate ln of stuff. That would differentiate to 1 over stuff, and so that's going to be 1 over tan x. And so that differentiates to, quite simply, sec squared x over tan x. And you're good. Okay, let's move on. Let's move on to product rule. How does product rule work? Well, product rule says if you've got y equals the product of two functions, both of which must be functions of x. Now, you might not notice the significance of that. All we're really saying is we're not dealing with all sorts of other variables in our calculus. but both of those are functions of x. Very important, that, really. But if that is the case, then dy by dx equals u dash times v plus v dash times u, where u dash represents a derivative of u and v dash represents a derivative of v. So this is actually, I think, even easier than chain rule. We can see in question 1 that this is perfect for product rule because we've got two functions. We've got e to the 3x and tan 6x. I hope you're comfortable with differentiating both of those individually on their own, because you'll need to be. But then we're going to get dy by dx equals, okay, e to the 3x differentiates to 3e to the 3x, and then we just times it by the other function undifferentiated, and then plus, and now we're going to differentiate the tan 6x first, which differentiates to 6 sec squared 6x. So let's write that down first. Multiplied by the other side undifferentiated, which is simply e to the 3x. Now I do like to point out to my students that it's always a good idea at the end here to do some serious factorization, because they always tend to factorize really quite nicely here. You'll notice that both terms have a 3e to the 3x in them, so I can take that out, and then I'm left with tan 6x plus 2 sec squared 6x. And if you really wanted to, you could rewrite the sec squared 6x in terms of tan, because 1 plus tan squared is sec squared. That could be really useful there for turning that into a quadratic in tan, and perhaps finding turning points on the curve if it does in fact equal 0, because you'll need to factorize the resulting quadratic. Okay, so that one wasn't too bad. And then let's finish off with the very last one, sine squared x. This one is obviously even easier. And I would like to point out here, I'm going to do this both ways. I'm going to do this chain rule way first. Chain rule way, because this is a function of a function, I am allowed to choose chain rule here. I could simply differentiate inside the brackets. I'd get cos x. Then I'd differentiate stuff squared. Well, the answer is 2 times the stuff. And so I'm going to get 2 sine x cos x. So that's one way of doing it. But we could also, if we really wanted to, we could use product rule, because this is a product, sine x times sine x. I could differentiate one side, and sine x differentiates to cos x, times it by the other side undifferentiated, plus differentiate the other side, and I'm going to get cos x times sine x once again. And if I've got cos x sine x plus cos x sine x, well, just as if I have a plus a, I'm going to get 2a there, which is 2 cos x sine x. And there you go. Right, let's move on to quotient rule. So, quotient rule. Well, this looks a bit more unwieldy, and it's given to them in the formula book, so you know, I'm not surprised here. Different exam boards actually give out different things in their formula booklets. Quotient rule tends to be one which is given. I believe product rule is sometimes given, sometimes not given. Chain rule they normally expect them to learn. But yeah, the way you'll see chain rule expressed in all the textbooks is, you know, as I write it, dy by dx is dy by du times du by dx. Anyway, I'm waffling a little bit here, so let's get straight into this one. This essentially says there is a little rhyme when you can learn for this. Low d high minus high d low over the square of what's below. That's the only way I remember it, really. I saw it in a textbook once, and it seemed like a sensible thing. What it means here is we take the low function and multiply it by the derivative of the high function, which is why we've got f dash of x, g of x first. And then minus high d low, well, that's a high function multiplied by the low function differentiated, and then over the square of what's below, that's the bottom of it. So you can learn that little rhyme if you like. Okay, now I'm sure you'll notice here that we are actually going to differentiate tan kx here. So in other words, we're going to prove that tan kx differentiates to k sec squared kx. So without further ado, let's have a go. dy by dx equals, okay, we've got low d high, so that's going to be a cos kx multiplied by the derivative of sine kx, which is of course k cos kx, and that's going to leave me with k cos squared kx minus, okay, now we're going to do it the other way round. We're going to differentiate the low term, and that's going to be differentiating cos kx. That's going to differentiate to minus k sine kx, which means this is going to turn into a plus, and you're going to be getting k sine squared kx, and then we're going to be needing to divide that by the square of what's below, which can be written as cos squared kx. I'll put the kx in brackets just to keep it away from the squared. Okay, I hope you recognise that we could factorise the k out the top, giving us cos squared kx plus sine squared kx, and that of course is equal to 1. So when we get the cos squared kx plus sine squared kx, what I can do is literally just cross it out, because I'm timesing by 1 there, over the square of what's below, and that is k sec squared kx, and we're there. Woohoo! Okay, hope you found those examples useful. Let's have a look now at a past paper question. Okay, so here we have y equals ln of y equals 3 ln x squared plus 1 over x squared plus 1. First thing we've got to do is find dy by dx. So naturally, this is a quotient rule problem, and let's do it with the little rhyme. Low d high. Okay, so low is x squared plus 1, but then we're multiplying that by the derivative of 3 ln x squared plus 1. Now, with the 3, it's a constant of differentiation. I call them constants of calculus. You can kind of ignore them and just put them back in at the end. So all we've really got to differentiate here is ln of x squared plus 1. Now when we differentiate that, we need quick chain rule, and this is my point about using quick chain rule. We need to differentiate inside the brackets, giving us 2x, and then differentiate ln of stuff, and that would be 1 over the stuff. There's a lot going on there. Oh, and we need to times by 3, so I'll just change that to a 3. Now notice straight away that actually that one's going to cancel with that bracket, leaving just 6x here. Quite a lot going on there. Minus high d low. Okay, right, so we're going to be multiplying by the high, which is 3 ln x squared plus 1, but we're also going to be multiplying that by the derivative of the low, and that's just 2x, and 2x times by 3 ln x squared plus 1 is going to be 6x ln x squared plus 1, all over the square of what's below, and that's x squared plus 1 squared. Now it looks really ugly the way we've written it down there, so let's actually tidy that up a bit. I'm going to put it just up here. We're going to have dy by dx equals 6x minus 6x ln x squared plus 1 all over x squared plus 1 all squared. And we're done. You could actually factorise the top as well, and that's exactly what we're going to need to do in part B. So let's actually look at part B. I'll write that down again in 1 second, because I want to generate some more space. So we know that we've got 6x times by 1 minus ln x squared plus 1 over x squared plus 1 squared. And we want to find the exact coordinates of the stationary point. Well, stationary points are found where the gradient equals 0. And as soon as you multiply the low there, the x squared plus 1 squared across, that's still going to remain 0. So what we really need to solve is 6x times by 1 minus ln x squared plus 1 equals 0. But it wants the turning point where x is larger than 0. And this first part, 6x, gives me x equals 0, because there is indeed a turning point, and you can see that on the graph at x equals 0. So divide that across, we can ignore that essentially, and we can just say, well, 1 equals ln x squared plus 1. We can get rid of the natural logarithm by exponentiating both sides. And then we can see, just by taking away 1 and square rooting, that x equals the square root of e minus 1. And we're all done. Actually, we're not, I beg your pardon, because it does say it wants the coordinate. And therefore, it doesn't just want the x value, it also wants the y value. Okay, so let's use this equation to find y. I don't need to use a calculator. You can do if you want, though. This is a calculator paper. We know that x squared is just e minus 1. So you're going to get 3 ln e minus 1 plus 1. Well, they cancel. Over e minus 1 plus 1. They cancel again. But what is ln of e? Well, it's just 1. And so you get 3 over e for the y coordinate. And you're good. Okay, so I hope that was useful. Just a quick reminder really of how chain rule, product rule and quotient will work. It can be a little bit awkward with the algebra, and what I say with it is, whilst it's easy to perform, it's also easy to make a careless slip. So be very careful when you do it, and make sure you're checking for sign errors, because let's face it, they happen a lot. Best of luck with the remaining part of the course, and I hope you've enjoyed the video. Take care.